So I'll give people a little bit of time just to get to join the webinar, and then we'll get started here in just a second. I think I've caught some kind of cold, so you'll have to excuse my voice being a little bit strange today, but I am not the main speaker anyway, so I hope you'll manage. Right. Okay, with that, I think we'll get started. So welcome everyone to day 2 of Understanding Latency. My name is Bjørn, Ivar, Teigen, Monclair from CUJO AI, and I'll be your host again today. So first, some quick reminders. The full agenda is available on the event website. And we had a series of excellent talks yesterday. Those are already available on YouTube. And if you go to understandinglatency.com, you will find direct links to each of the talks. And I think by now we have almost all of the slides there as well. So you can go there and find things if there's anything you're looking for. I think as well that the chat should be working today so that you can talk amongst yourselves while the speakers are talking. And then just a reminder as well, please use the Q&A for questions. If you put the questions in the chat, it quickly becomes a bit chaotic and hard for me and for the speakers to keep track of what questions have been asked. So if you look at the bottom of your screen, there will be a Q&A button which you can use to submit questions. And I mean, I will try to catch any questions in the chat as well. But if you want to make sure your question gets to me and to the speakers, please use the Q&A function. And as always, we're also recording, and the Q&A will be included in that recording. So any questions you ask will be part of what is made publicly available after the event. Okay, and with that, let's jump straight into the first talk. Our first speaker today is Jason Livingood, Vice President of Technology Policy and Standards at Comcast. In this role, Jason coordinates Comcast's efforts to develop open standards, such as at the IETF, spur R&D through efforts like the Comcast Innovation Fund, apply research and standards into new network and services concepts and deployments, and engage with governments, regulators, and other stakeholders. So Jason, welcome.
Thanks, and hopefully you can see these slides okay. I'll assume so.
We can, yes.
Perfect. So I'll say two things at the top. First, this slide deck is intentionally provocative because I'd like to spur re-examination of long-held assumptions. And then secondarily, some of this is peppered with my own opinions, which may not be aligned with those of my employer. So let's jump right in. The first is that in today's internet, you really, and ISP networks in particular, you get what you measure. And so around the world, there has been for many years now an emphasis on speed tests, and therefore you get a lot of bandwidth capacity to show good results on that. This wasn't an accident. For many years, increasing last mile capacity for users was correlated to increases or improvements in user quality. But that linkage has really broken, and that's changed. So the question is really, what is next? And thinking about what is next, I think the first thing is sort of declare bandwidth victory, as it were. Say we have won the bandwidth war, and we're ready to move on to the next battlefront, as it were. And that is the reality that we're in now, which I like to call the post-gigabit era. And this is an era where many users have 1 gigabit per second at home, and network bandwidth does not constrain end user QoE. Really, the only things that are using 1 gig, even just for a few seconds, are speed tests, which I think are becoming a little bit like pollution on the information superhighway. But if you look at the apps that users are really shifting to today, those are highly interactive real-time apps. Those really do not use a lot of bandwidth or require a lot of bandwidth. And that's not the key QoE stat. Here's another example, thinking about, the gigabit per second that many people have at home. At a recent IETF meeting, 820 devices, and even there, they were only just going over a gigabit per second downstream, and half that in upstream, and their averages were quite low. So even in an environment with hundreds of users, the demand did not exceed the capacity that many users have in their homes today. And so this is a key slide. I think it's important to sort of internalize that we are in an era of bandwidth abundance, not scarcity. And a lot of the ways that we think about networks and how to make things, quote, go faster is really predicated in an assumption of scarcity. And you can see this even in policy framing with regulators, where they talk about paid prioritization as one of those net neutrality sort of things. That again is grounded in assumptions of scarcity. Again, where quality of service marking and relative prioritization made a difference. But we're in an era now, as I said, of bandwidth abundance, and applications are no longer limited by the access bandwidth that the users have. And so I would say, it's time to really forget about quas, to forget about prioritization, stop thinking constantly about bandwidth, stop talking about volume of data transferred over some period of time, and instead start to think about the latency of the network, the jitter, the responsiveness, which are really the new concepts. CAGR, the compound annual growth rate of internet capacity in the last mile for many years was growing at like 45%, and that's really flattened out tremendously. And I think what I would observe is that the capacity, or the supply in this case, has really decoupled from demand on the usage side. Again, because applications are not out there that require that amount of bandwidth, and there simply aren't enough users or devices stacked up in a home network that use that much bandwidth. And so what you find, I think, as an economist would describe, is that the bandwidth supply, additional bandwidth, has very low marginal utility, but other things probably do. So you can see this, as a really great chart from years ago, from Mike Belshi. Page load time isn't really improving as you increase bandwidth, but as you improve and lower latency, it does. And so this was, I think, an early signal that there are other things there. And I think this is, I won't go into this chart in too much detail, but I think this is a part of a shift in sort of the era of the architecture of the internet that we're in. I think the first era of 20 to 30 years was all predicated on this notion of file transfer. You were uploading or downloading, and all of the metrics were about, how long would it take to download, a game of X size, and even video streaming, where you're downloading little chunks of video at a time. Now we're moving into an era, already in an era, arguably, where it's completely real-time oriented, and those require different kinds of measurements, different kinds of metrics, and networks being designed and deployed in slightly different ways. As a quick update, speaking of network deployment, on the Comcast network, we deployed low latency DOCSIS, which is several things for us. It was downstream AQM. That covers all of our CMTSs, cable modem termination systems, covering about 20 million homes today. And we also have L4S and NQB from the IETF that are part of the LLD standard. I'm sure Greg White in a moment will talk about some of those things. And that's now to 9.3 million homes and growing every day. And we saw dramatic reductions in latency and jitter. Certainly downstream AQM helped. That was meaningful, but dual queue, really, we've been able to move working latency upstream and downstream to very close to idle latency, and in particular, dramatically reduced the jitter so that we've got highly consistent latency, which is great. And we support a wide variety of consumer devices. You can see the list here. Some of these just got enabled overnight. Um, we talked about the network, the access network, and the internet, and we talked about the bandwidth is not an issue there as much. However, within the home network and the wireless LAN, bandwidth remains an issue, as does delay. And this is an important new frontier. And so one of the things to really think about and sort of internalize is that if you talk to an end user, a consumer of internet services, they will attribute home Wi-Fi issues to their ISP, even though the ISP may not control that Wi-Fi access point. And as you can see, as I mentioned, we're sort of in this post-gigabit era. We've got, if you see, over 800 megabits per second on the right-hand side for upstream and downstream to the internet. The prevalence of a Wi-Fi bottleneck then being in the home is pretty much 100%. So you can see that in many users' experience today. So we've experienced a lot of issues, lots of random things that people report to us all the time. Many of those things users simply do not know how to solve. And in most cases, the user is not aware of those issues. So that's sort of the next front. I won't spend any time on this slide other than to say this is stuff that the CUJO team's working on, through the old Domos software to try to characterize home network performance and try to guide people to how to repair those things, how to improve them, etc. And I think that the key shift is this first bullet, which is this shift from network operators thinking, I am delivering X bandwidth of service to a home router or home CPE DMARC of some kind, to being better aligned with what the users think of. How is the application experience on a particular device, on a particular location in my home at a particular time of day? And what does that, really look like? And, so that's the sort of next slide here, which is to say that you know, ISPs have added tremendous amounts of bandwidth. They've dramatically improved network reliability, and yet end users are still unsatisfied in some ways. And I think my personal view is that on the second bullet, the idea that the ISP has as of the service definition and what the user have are in conflict. Users, as I noted on the last slide, are really thinking about how does this particular application perform on this device, say on my iPhone or my iPad or my laptop or my set-top box at a particular time when I want to use it, etc. Not, oh, I ran a test and it said I had, 1 gigabit per second, but I'm still having problems. And so, I think that in the ISP space, there's a lot of evolution needed to rethink that notion of service delivery, especially as we take into account these non-bandwidth or non-access bandwidth types of attributes to a service. Not sure what to call that, but it's something a little bit new. And I would say from an ISP standpoint, we often think in terms of like reliability engineering, which is about maximizing uptime and availability. Network engineering, which is about, the megabits per second and the milliseconds and the jitter. That's a sphere that I'm comfortable with and I live in day to day. But there's probably this gap where the user expectations and the ISP service concepts have to become better aligned. And as I noted, just previously, it's sort of a composite of all of these functions all the way up the stack at layer 7. And it really thinks about, what those applications are performing like over time on every device to every destination. And I think that's where there's an opportunity from a user satisfaction standpoint. So just to sum up here, I think we're in an era of bandwidth abundance, not scarcity. We have to start to change a lot of those assumptions, which even go to like the spinning wheel icons in a lot of applications. the users really face an issue with latency and jitter, not bandwidth. Of course, the Wi-Fi network, remains a significant challenge. How to close that gap is a big question, and one of the things that I think this webinar is exploring. So that's it. Happy to take any questions.
All right. Thank you very much, Jason. I do have a question. I think I really liked what you said about the user and ISP idea of service definition not being aligned. And I'm wondering, do you see a path to aligning those ideas?
I certainly do, and I think that's in the and ISPs have been trying to do this for a while, but perhaps not fully, but trying to push that demarcation line all the way down to the per device level. So sort of, not just thinking, oh, I'm giving somebody that's you know, a layer two interface device to our optical network or something like this, or to our DOCSIS network, a cable modem, and thinking, I'm providing that plus a Wi-Fi, gateway and maybe extenders, and I'm able to tell you something about the quality level to every device on the network, and being able to troubleshoot those on an individualized basis.
So you think it's more about changing how the ISPs think about it than changing how users think about it?
For sure, yeah, and I think that there's some, user evolution of their views as well. But I think you need a proof of concept of ISPs successfully delivering improvements in this space for user to say, oh, maybe I shouldn't run my own home access point, which is 8 years old or 10 years old or something like that. Maybe it's better if it's part of a service that I buy, because it's part of this internet delivery service chain, if you will.
Yeah, makes sense. All right, and we have a question as well from Satish Mudugere. Um, how can we align all ISPs to understand the bandwidth abundant era? Pointing out that ISPs are competitors among
Well,
themselves, but
yeah, I think one of the reasons it necessarily changes is because we now have in most markets, I'll use the US as a comparison, 4 or 5 or 6 competing providers using 5G wireless, DOCSIS, fiber to the home, etc. And all of them are providing multi-hundred megabit per second services that will meet a user's bandwidth needs. Um, but not necessarily all of the same latency attributes. Um, but suffice it to say, if you have a lot of services where the user's bandwidth needs have been met, then the question is, what are the other bases on which you are differentiating your services? So I think we're sort of entering this era where the network operators are forced to do more innovation and more differentiation. And one of those ways is, better quality control over the end user Wi-Fi experience.
right. And there's another question as well. So Wi-Fi is a challenge since the client isn't under your control. How do you think about measuring that leg of the network?
Well, some ISPs, including Comcast, already have an app that users can run where it runs what we would call multi-leg test, where it's looking at performance not just to the gateway, that's the DMARC, but from that point all the way inside the network to devices. But that's not the same as looking at what application is running on that device. And of course, where that device is moving throughout the home over the course of an application experience. So I think some ISPs are doing a little bit to do some diagnostics there, but there's a lot of innovation, I think, yet to come, a lot of opportunity there.
All right. Thank you very much. And I see multiple questions both in the chat and in the QA tool now, but I think we do have to move to the next speaker. So if you have time to answer the questions in the chat, that would be much appreciated, I think. So thank you very much again, Jason. And next is Koen de Schepper, research principal at Nokia Bell Labs. Koen's work spans fixed and wireless, home and access networking, with a focus on improving latency and scalability of networks and applications. And he's a co-author of the L4S IETF RFCs. So Koen, over to you.
Thank you. I guess you can hear me and Should be able to see my slide coming up.
That is working.
Okay.
Perfect.
Okay. Thanks, Jason, also for introducing today the low latency concept. Maybe one thought related to Wi-Fi. I completely agree that that is one of the bottlenecks. And there is not only innovation needed to kind of manage applications and maybe again going into the quality of service, it is so much more the opportunity to improve the Wi-Fi physical layer, the scheduling and other things, and we are working on that. So that's anyway, fully agreed that there is a lot of innovation possible. Anyway, going back to my presentation, trying to find, okay, it's working. Trying to move a slide. Okay. Maybe a small warm-up also before diving into the topic of today. Haven't really talked about it, but this is about opportunities that come from Alvarez and from Prague that we still think too much in AQM, and there's another alternative which is made possible because of Prague not needing a queue in the network, which is what I call ARM, and that's the topic I want to introduce you. But before that, a small warm-up, maybe also related to the discussion about how do we sell latency. But the question is typically asked, is 300 megabits faster than 3 megabits per second? And actually, it's a weird question, and people should say, I don't know, because if you sell a car and you say, or a vehicle in general, it can do 300 kilograms per second, or the other one can do 3 kilograms per second, what is the fastest one? You shouldn't also not be able to say, I don't know. And if you compare, let's say, this capacity, it's actually capacity in kilograms per second, how much can you carry? If you look at examples of vehicles, then 300 kilograms per second is the top vehicle, container ship, and the 3 kilograms per second is an airplane. And if you ask me what is the fastest, I would know. It's the bottom one, although because I usually only need one T-shirt from the other side of the world, and that can be delivered in 12 hours, and the other one is in 30 days. And you can imagine where my T-shirt would be positioned in this ship. It's probably not on the top of the container, but somewhere deep in this container. So you can imagine what's the fastest. But a small note is that when you need more than 9,000 tons of T-shirts, it's actually becoming faster to use this vehicle. And maybe next time people ask you how fast is your internet, and you say it's 10 milliseconds, I can deliver a message in 10 milliseconds and get an answer in 10 milliseconds. And then they say, no, I mean in megabits or gigabits per second. Then you can also say, I don't ask you how fast your car is in kilograms per second, right? Anyway, small warm up. Going back to the topic, it's related to how networks can control the rate of applications. And I have done a talk in the past about what's the difference between classic, the main difference, how to control rate. And in today's networks, it's all about schedulers that control the rate. They have a weight, and different users are scheduled. And fairness is done by schedulers, which create a queue, which blocks packets and create a queue. And that is needed to design the networks in this way, because in the past, classic really needs a queue to control the rate. Even think about BBR is delay based. It will not slow down if it doesn't see delay. It only starts going at a lower rate if the delay is bigger than 30 milliseconds. And so there are so many more reasons. And in a past presentation, I explained also that we removed all those reasons in the Prague congestion control, and that the Prague congestion control doesn't need the network to build a queue. It can do this rate control purely with marks. And of course, if the network wants to create a queue for other reasons, it still can do it, but it shouldn't do this by default. And it shouldn't be, let's say, a force of habit to design networks for Alvarez at least, in the way we did it in the past with schedulers and blocking and creating queues, and then put an active queue management on top of it. I also did a talk in ICCRG before to explain also how applications can be fully non-blocking, and that if the network, even your interface or internal processing would do marking end-to-end, that it would be very nice with, for instance, this ProcCC library, which is open sourced and can be used in applications to get feedback from the marks from the network. You feed them in here, your round trip times, how many acts you received, and it will generate, like the TCP proc, exactly the same, a pacing rate, a window, packet burst you can use also if there is bleaching in the network. But the main important thing is also that you can, with that pacing rate, you know the rate that the network can sustain, and you can generate your payload with that pacing rate. So, for instance, a video encoder can use that CBR rate, constant bit rate. It can be adapted all the time to generate fresh frames. And you have a non-blocking system end-to-end and a single non-blocking mechanism. You don't have to worry about flow control and so on. Anyway, to introduce rate management, we'll start from the dual queue to give you an idea that the dual pi square is not an AQM all the time. It's partly an AQM when it needs to be an AQM, at least for classic, it's always an AQM, but for Alvarez, it's only an AQM when it's really needed. Because if there is classic traffic, it's actually not the AQM of the Alvarez itself, it's the AQM of the other classic traffic that drives the rate of the Alvarez flow. So there is no queue. And that's why proc needed to be as much as possible controlled the rate without the need for queuing, because if there is a standing queue, it would block completely the throughput for classic. And we want to give here priority in the scheduler because we want to have low latency. And so in this mode, there is never a queue, and still the Alvarez could be controlled with the rate. The only thing is, of course, if there is no classic, then we have here a physical limit, and then we might build a queue. And as long as this is a stable physical limit, then it's pretty okay to manage a very small queue here with proc. But if it's a variable bandwidth, you'll see that for wireless networks, like also Wi-Fi, but other wireless networks or big shared networks, a scheduler can really do quite a lot of harm, and throughputs can change a lot, and that creates big latencies. So that's why we talk about headroom as well. If we can keep headroom and we don't meet that physical limit, that's an advantage. Maybe to give you a small impression, what I mean with headroom is that, okay, if we have here a physical limit, which might vary here, this is the physical limit which goes up and down. As long as it is classic, the Alvarez flow can go at a pretty steady rate. It might have some peaks in throughput, which can be absorbed. It gets priority here, so there is no queuing latency. Also, if the throughput drops, it's mainly the classic rate that get queued a little bit longer, millisecond more or less on a queue of tens of milliseconds. Nobody cares about that from an Alvarez perspective, from a classic perspective, but Alvarez might not respond immediately, would otherwise also be queued, but now it will reduce a bit later. And that's where instead of doing the reduction here, it's just moved a little bit further. So on average, the classic gets the same throughput and Alvarez gets also the fair throughput, but it has headroom, and this headroom can be filled with data that is in a buffer and is immediately ready to be transmitted when rates go quickly up. So that's a bit what I mean with headroom, and the headroom can be used. But of course, if there is no classic traffic, L4S don't necessarily want to use this up and down going, because every time down you will see we have quite a big latency spike. So it's good to avoid too jittery traffic if you want to keep your latency low. So yeah, as long as there is classic traffic, we're actually running in some what we call an active rate managed mode. And as long as the classic usage is enough, let's say, to create headroom, we will never need to queue L4S packets. And if there is no classic traffic, we could create headroom, which is then not used. But that's the advantage of using then the L4S. We can have consistent low latency, and the network can provide headroom so that variations won't hurt it. On the other hand, if classic is used by the application in parallel, potentially it can use this headroom. But the talk of today is not about mechanisms how to provide this headroom and how to have potentially other policies and how to do or determine the rate. I just want to show you today how efficiently the rate can be managed if you control that rate with, for instance, a policer. And to give you the difference, this is how normally networks today typically are managed. We have a scheduler or a shaper, and let's assume we can shape, or we do want to shape that rate for a certain time to 25 megabit, then 100. So it's a 4-time increase, 200, 400, 800, and then we decrease by half, 4 times reduction. What's the impact on the latency and how quickly do we follow those rates? That's the first question. With today's schedulers, it could be like a flow queue where each user here we have like, I don't know, the physical limit is 10 gigabit, which is what we have today typically in PON systems, in DOCSIS systems, even in Wi-Fi today. The physical air rate is very high if you want today. 5G, so we are gigabit speaking, and our applications typically use this range for our video streaming XR applications. There are no interactive applications that today, at least, that use 800 megabit. So we have a lot of headroom, potentially headroom. And let's see here even a reduction of 80 times 8, so it's 640 times reduction, instant reduction, and here at very low rates. And compare that. So here we have, we would use a dual pi square with a 1 millisecond step and a 50 millisecond. If the queue grows up to 50 milliseconds, also pi square will start trying to manage it. And at the end, drop the packets. Base delay is 10 milliseconds. This is the experimental setup for the first tests. And this is when we would use a policer to control the rates. And we would be able to have headroom up to 10 gigabits. So might be more of those users in that 10 gigabit. But we decide this is just an artificial pattern, but of course there can be other patterns based on whatever policy you want. And here we go even down to 0. That means we ask to go to 0, and we mark all the packets which are above 0. So 100% is marked here. And the other cases, it's only 2 megabit, 5 megabit, 80 megabits are not marked, and the rest is marked. This is a bit how the policer work. So policer is not shaping, it's not stopping the packets. The priority scheduler is also not stopping the packets, so there is never queuing, and that is the advantage, that you never see queue, but you still can control the rate. And let's just see how good it can, or how bad it can do that. So first experiment is an active queue management. We were stepping from 25 to 800 megabit, and then going down to 25 megabit. This is active queue management. So this is latency, this is the rate, and this is how much marking is done. So the rate goes 25, it's immediately can go to 100 here. This is really blocked and enforced by the shaper. It cannot go over it. So First of all, you see here our latest proc in action, which is here you see especially going from 400 to 800. The previous proc was going slowly up like this, extending this line here. And now if we don't get marks within a certain amount, we start growing by 1 millisecond per round trip time. And you see here a little peak, 1 millisecond extra latency, because here we have the step marker of 1 millisecond, which marks the packets with different marking probabilities. And okay, everything goes well going up.
Koen, we are close. We're a bit over time now, so we have to wrap up the talk quite soon.
Yeah, I saw we already were late. So anyway, so it's the main thing is reducing here. You see there are latency spikes, which going down from a factor of 2, 10 milliseconds packets in flight, we will become 20 milliseconds. So we get here a queue of 10 milliseconds. If we reduce 4 times, it's creating a queue of 30 milliseconds. This is with active queue management, and this is very harsh conditions that typically it's not that worse. But anyway, with active rate management, you see, of course, going up, we can also go quickly up. We overshoot instead of 1 millisecond extra latency on the 1 millisecond threshold. We have just a small overshoot in throughput, but for the rest, it's following the throughputs. The latency, you see, stays below 50 microseconds or around 50 microseconds. There are some peaks, but that are artifacts of our capturing. And then you also see when the throughput goes down, we start marking a lot, but we don't delay the packets. And actually, if you see the queue that we get takes longer than the reduction in the rate if we just let the packets go, and we can let the packets go. It's only a big marking, and it goes even faster than if you look at the queue latency here is around the same timing here, but it has a big application impact. This is the result for going down this 640 times down in rate. It would have created a queue of 600 milliseconds, but because of drop, you see it also goes within 3 seconds down. With active rate management, it is within half a second, a few hundred milliseconds, it's going down already to the 100 megabits per kilobit, very nicely, 100% marking. And you see it's the latency is below 80 milliseconds, microseconds. And at very low rates, it also, with the queue, it takes 3 seconds before the queue is drained. With active rate management, the rate is reduced within a few hundreds of milliseconds. To wrap up, I'm not going to in detail in this anymore. It's kind of what I said. Maybe one insight you have to read is the difference between FQ, which is a scheduler, and an AQM per scheduler, and that's the difference with dual queue, which is then a marker and it's not blocking per se when it's running in ARM. Some slogans that need some change. Shapers are good and polices are bad for TCP, which has to be changed now. Shapers are good and polices are bad for classic congestion controls. For alpha-REST, polices are good and shapers are bad. AQM is the best to control classic latency. Actually, ARM is the best to avoid alpha-REST latency. ARM is better to, and it because it directly controls the rate. Dual pi square is an AQM, is often said, so it's sometimes an AQM, I would say, and it's sometimes an ARM. In the future, I think, well, we definitely work on networks that use ARM instead of scheduler if it's possible, and applications will need to implement all proc requirements and maybe just use UDP procs to manage their rates. Use them in parallel classic and alpha-REST when it is depending on whether it's best or for their data chunks, whether they need this higher throughput or that the latency and they can wait a bit, or that they really need this interactive experience. That's it from my side.
All right, thank you very much, Koen. We are a bit over time, so any questions will have to be answered in writing, I think, but I see at least one question in the Q&A. So thank you very much. And next is Mohit Tahiliani, Associate Professor of Computer Science and Engineering at NITK Surathkal, India, and a board member of the India Internet Engineering Society. Mohit's research spans network congestion controls and queue disciplines, and his team's work on packet scheduling to address buffer bloat was merged into the Linux kernel. So Mohit, welcome.
Thank you. I hope you can hear me.
I can, and I also see your slides.
Perfect. Thank you. So hello, everyone. I'm Mohit. I'll be talking about the work that we have been doing on building an algorithm called FlowQPy. In short, we call it as FQPy. And like FQCodal, it's a hybrid packet scheduler and active queue management algorithm. I'm from NITK Surathkal. It's a university in India. And before I get started with my talk, I would like to thank all my students who have been working with me on this algorithm, and it has been quite a few years that we have been trying to build it. So credit goes to all my students and collaborators for what the work I'm going to present today. So just a bit of an overview of FQPy before I get into some of the experimental results that we have been carrying out these days. It's basically something which is similar to FQCodal. So it combines flow queuing with the PIE algorithm, which is the PI controller enhanced algorithm RFC 8033. And as I mentioned, it's pretty similar to how FQCodal combines FQ and Codal. And the functioning is pretty much similar to RFC 8290 when it comes to the flow queuing aspect of it. So what we do is we have these incoming packets that are hashed into buckets, and each of them have its own queue. And later we dequeue them using a DRR-based kind of packet scheduling algorithm. So long as the PI algorithm is concerned, as a part of FQPy, it is pretty much similar to the RFC 8033. However, we suggest one modification in our work. The RFC 8033 originally proposed two ways to calculate the queue delay. One was by using the departure rate estimation, or we call it as Little's law. And the second one was something similar to what Codal does. By using timestamps, attaching the tags at the enqueue time, and then during the dequeue time, you kind of take the estimate of how much the packet waited in the queue. So we recommend actually using timestamps, and we have been also working on comparing the results of how we see the difference when you calculate the queue delay using timestamps or by using Little's law. And there are three implementations of FQPy in case anyone is interested. We have FQPy supported in Linux, and we have distributions like OpenWRT supporting FQPy. It's also available in FreeBSD and the Network Simulator 3. A bit on the evaluation of the PI controller. So the original idea dates back to 2001 when early control theoretic AQM was proposed by Professor Vishal Mishra. Later on in 2013, we had the team from Cisco working on RFC 8033, which is called the PIE. We already saw PI square. So PI square work came around 2016, and around the same time frame, we also started working on FlowQPy. So this is how the algorithm has in general evolved. Talking about the current status of FQPy, so this table just shows that we have all the algorithms like Codal, FQCodal, Pi, FQPy, and we have Linux and FreeBSD implementations of all of them. So long as the specifications are concerned, we do have specifications for Codal, FQCodal, and Pi, but there is none for FQPy, which is what my team has been working on. And recently, during the ITF 124 at Montreal in November, we had the FQPy internet draft adopted by the TSVWG. So if you are trying out with FQPy, we'll be happy to collaborate with you. We have conducted two sets of experiments. The first set of experiment is related to NS3 simulations, and the second set of experiments are related to the live experiments that we have performed. This particular chart shows the different set of experiments that are performed using a tool called CCPerf. Unlike iPerf and NetPerf, this tool is actually not on the live systems. It is based on NS3. So you have the base as NS3, and on top of that, you have CCPerf. And the boxes that you see colored in blue are the ones that are compliant with RFC 9743, which is an RFC that describes how you should go about testing congestion control along with queue management algorithms. And the ones that you see in the green are the ones that actually we have completed performing the experiments. Most interestingly, the ones are related to where we have a pulse wave where either the RTT is oscillating or whether the data rates are changing. So for example, this is one plot which we have, and the paper is linked at the bottom of the slide, but we wanted to see how FQCodel and FQPI perform when you vary the RTT. So on the left-hand side, both the plots related to throughput and queue delay are when you increase the RTT, and on the right, you see the plots when you decrease the RTT. One observation that we had, as you can see on the left-hand side plots, is that FQCodel was having periodic throughput drops, particularly when RTT was varying. And when we looked at the queue delay plot, we actually saw that the queue delay was literally becoming empty. You can see those flat blue color lines at the bottom in the queue delay plot that shows that there was no backlog in the queue. It was totally zero, which is actually, that is something that was hurting the overall throughput of the network. And FIFO plots are just for representation purposes in the paper to show that how bad it can be without AQM algorithms or any kind of queue management. We didn't find a lot of problems, and we could see that both the algorithms were performing pretty much as expected when the RTT decrement was happening. One point to note here is that Codel typically uses 5 milliseconds as a target delay, whereas PIE, the RFC 8033, recommends 15 milliseconds as a target queue delay, and we continue to retain 15 milliseconds in FQPI as well. That's why you would see FQPI rotating around 15 to 20 milliseconds, whereas you will see FQCodel oscillating between 0 to 10 milliseconds. So that is as expected behavior. We also had another experiment where we periodically changed data rate very often. And on the right-hand side, the plots show the point where we fluctuated the RTT. And again, we observed some problems when particularly RTT was oscillating. We could see throughput falling down sharply with FQCodel. Again, we saw that the queue was totally draining out and it was becoming zero, which was overall hurting the throughput. On the left-hand side, you can see when the data rate was oscillated, particularly the data rate was increased from 15 Mbps to 60 Mbps. We could see that there were some issues with FQCodel in catching up with the available data rate. It was not able to utilize it, but we have been working on solving that problem as well, which is not in this talk, not in the scope of this talk, but there's something that we are looking into it, and we have some preliminary results which will be soon publishing about it. Moving forward, we also plotted a time series graph, and we again have a similar pattern which we can see with FQCodel, that it wasn't able to saturate the throughput when it was available, and also it had a lot of a jittery behavior when it particularly had any kind of oscillations happening in data rate or RTT. So it was oscillating between its target queue delay all the way up to 30 milliseconds. We did not see that behavior a lot with FQPI. Again, we have probably understood why this is happening with FQCodel, and while we continue to work on FQPI, we also intend to see if we can make FQCodel a bit better in terms of this particular behavior. We conducted second set of experiments, which are live experiments. They were further categorized into two sets. One experiment was conducted at NITK Surathkal, and one experiment was conducted recently at IETF 124. And we used the RUL test using Flent, and thanks to Quantum Networks, who provide us their access point to us for testing, the QQIW235. And we could see both the algorithms performing pretty much similar, just that we had little more jitter that we could observe with the Codel part, but a little more stable behavior with FQPI. And again, these all results are documented in the paper that is linked at the end. So those were the primary set of results that I wanted to discuss. And before I wrap up my talk, just would like to spend a minute to thank Dave Tart and remember him today, because when we were actually working on FQPI way back from 2016 to 2017, we used to have a lot of discussions with him, and he was the one who also agged our work when it was being pushed to the Linux kernel. And it was a big loss to the community, and also at a personal level. Just last year, I had met him at his boat in USA, and that's the email that I got last from him when I was about to publish the FQPI internet draft to the IETF. I wanted him to take a look at it, and he looked at it, he gave me feedback, and then later, when I submitted a revised version, he said, Mohit, put it on the bloat list, and it was a great suggestion. I got a lot of inputs from there. So we'd just like to take a moment to thank Dave for all the wonderful work that he did and the community that he built, and all the kind of support that he has extended to me as well as my students. That's it from my side. Thank you very much to the team for giving us an opportunity to present this work.
Thank you very much, Mohit. I do have a question. So I was wondering about the 15 millisecond queue delay target. How is that chosen? Is that to sort of choose a higher throughput level?
I think it was to ensure that the link utilization remains intact and the throughput doesn't get, the link utilization doesn't get impacted. Like one of the things that we have been trying to do is trying similar kind of target latencies with Codel. Like the spec says that Codel can operate at 5 milliseconds or should operate at 5 milliseconds, but we are trying to run Codel with 10 milliseconds and 15 milliseconds to see whether indeed a lower target value is the reason for such a kind of low utilization. And is that the reason why it's not able to catch up on the throughput when actually more data rates are available?
Got it. So those comparison charts that you had, were those with the same target delay or with the default ones?
With the default one. So the paper that we recently published was considering everything default, because when the user would use it, they wouldn't know that they have to change the target latency in any of the
Yeah. Makes sense.
We wanted to first try with the default, have the observations, and then start looking at what we can do to optimize it and give some feedback.
So what happens when you change so the target latencies are the same? Is it still a big difference in throughput between them?
Yes. So there is an improvement, but there is a fundamental design challenge that we identified with the Codel design, and we are tweaking it a little bit. And maybe next year, if we get a chance to present again at Understanding Latency, we'll come back with results of optimized Codel.
All right. Well, thank you very much again for presenting. And
Thanks.
next, we have Greg White. He has been a technical leader at CableLabs since 1999. He led the development of low latency DOCSIS technology and its associated IETF standards, enabling applications to achieve ultra-low round-trip delays, even at high data rates, a critical advancement for modern network performance. So Greg, welcome.
Thank you, Bjørn. Let me put my slides up. All right. So 2025 was a big year for L4S. And so I wanted to take the opportunity today to give a shout to the organizations and companies that helped make it a success this year. And also to give an update for others who've maybe been watching this unfold over the last several years. As I think everyone is probably aware, L4S involves some functionality that exists in the application, and it also includes or involves functionality that exists in the network. And there's no benefit to having the application support if there aren't networks that support the L4S functionality, and vice versa. There's no benefit to having networks that support L4S if there aren't applications that take advantage of it. So this has been a process, kind of this chicken and egg problem to get deployment going. But I can say, as of this year, we've definitely hit the critical mass and with some major deployments and major announcements. So, all right, let me jump into next slide. So, where do we want L4S to be implemented and deployed? Where is it most important? And as I mentioned, the applications are one piece. We have to have the applications that support the functionality and take advantage of it, but also in the network. And it's really at the network edge. So we're talking about focusing on 5G, focusing on DOCSIS and PON, as well as Wi-Fi, getting support in the edge of the network where queuing and buffering of packets happens most frequently. Certainly, it can happen other places in the network, but it happens most frequently at the network edge. And so that's where a lot of focus has been in the industry in getting support for L4S into network gear and into deployments. So a quick summary of some of the announcements and public information around deployments in networks. Comcast, you just heard from Jason Livingood. They're at over 9 million subscribers that have L4S support today, and growing. That's through the low latency DOCSIS functionality. T-Mobile this year announced a network-wide deployment of L4S in the United States. So both of those deployments happened this year. There are also other smaller network operators that maybe didn't make quite as big a splash when they rolled out L4S support, including NITK in the United States. And then there are many others that are in field trials and likely will be going to deployment in the coming year. And we've seen implementations across all the network technologies that I listed on the previous slide. That includes DOCSIS, many implementations in different DOCSIS equipment components. Seen it in PON equipment, seen it in 5G RAN gear, as well as in Wi-Fi. And specifically on Wi-Fi, recent news in 2025, the current draft standard for what will become Wi-Fi 8, so that's the 802.11bn draft standard, includes support for L4S. There's a link there on the bottom if you're interested in seeing that text. It's an optional feature, as are almost all of the new features that get added to 802.11. But expectation is that we'll see lots more Wi-Fi equipment adopting L4S as time goes on. But there's no need to wait for Wi-Fi 8. The Wireless Broadband Alliance published an implementation guidelines document early this year, which provides a set of recipes, I guess, around implementing L4S in a Wi-Fi 7 or even Wi-Fi 6 access point. And so that's I've been told one of the most popular documents that the Wireless Broadband Alliance published this year. On the application side, this is a summary of the application implementations that I am aware of, and this is all based on public information, but information that may not be easily found unless you know where to look. So I thought I'd bring it all together on this slide. We have both sender side and receiver side listed here because those are two different functionalities. So when you think of an application that, for example, to take the first one on the list, Apple FaceTime, the sender side would be the video stream and audio stream, which is adjusting its data rate based on received congestion signals from the network. And the receiver side is getting those congestion signals directly from the network and then sending feedback to the sender. And so those are two different functionalities. Obviously, they're both required for the sender to be able to adjust its rate. And you see Apple has been very public about their support for L4S and use in their different network protocols. Ericsson Scream, along with further down the list, Nokia's prod congestion control modules, both are available for applications to make use of as libraries to implement L4S. News around Google's implementation. So the version of Quick that ships in Chrome supports the receiver side, so sending the congestion feedback. The sender side is still in beta. And then on their server end, all of the public-facing servers at Google support the receive side of L4S, so sending that feedback from Quick. Linux TCP. Currently, you can get L4S support with some kernel patches, but we're working on getting that into the mainline kernel. I've got another slide that gives some updates on that. Netflix Cloud Gaming has been doing a lot of testing around their L4S implementation. I mentioned Nokia. NVIDIA has been deployed with L4S support for some time now. And the last two, Samsung on Android devices, so they implemented via an eBPF function, the ability to support accurate ECN for TCP, even when the Linux kernel doesn't yet support that, at least in the mainline kernel. And then last one, WebRTC. This is a big one this year. The receive side support, RFC 8888, has been deployed. So all of the implementations, it's effectively all browsers when using WebRTC, support the RFC 8888 feedback. That's been tested, interoperability tested with the NVIDIA GeForce Now and Netflix Cloud Gaming. And then the sender side, so that if you're on a video conference using WebRTC, to have that use L4S. There's an experimental version of that using the Scream v2 algorithm, and that's now available publicly in the Chrome Canary build. So lots of great work this year on implementation and deployment on the application side as well. For Linux kernel support, recent work has been on getting the dual pi squared implementation into the Linux kernel. That work is done. That was accepted with the kernel 6.17. The current work is on accurate ECN, so getting that functionality into the TCP stack in Linux. And that got broken into 3 different patch series. 2 of those have been accepted, and the third one is underway. And then the last piece is TCP prog, so the L4S enabled TCP. And that is just waiting in the wings for the accurate ECN part to get finished, because of course you need the accurate ECN for TCP prog to function. And not mentioned on the slide is that FQCODL actually was the first introduction in Linux of L4S functionality. That actually was adopted in kernel 5.16 about 4 years ago. So FQCODL has had L4S support for quite some time. All right. So for applications that maybe aren't L4S aware yet, how can they get there? How can they bring their application up to the modern state? So with a real-time application, there are some options. An application developer can design their own L4S rate controller, or congestion controller. There are requirements, the prog requirements in RFC 9331 that the implementer can follow. That's just kind of a starting point, but it's a fair amount of work, honestly, to develop a performant L4S rate controller. Probably a more expedient path would be to use one of the existing high-quality open source libraries, either the prog CC module or the Scream v2 module. Both of them can be integrated into an application and very quickly give L4S support to any real-time application. The congestion feedback side then on the receiver, that can either be using the standard RFC 8888, or if the application already has some proprietary means for getting feedback from the receiver, they can integrate that effectively just reporting back a count of the received ECN values. And then lastly, TCP and QUIC applications, which a lot of times people think of as being less latency sensitive, but in reality, they are very latency sensitive as well. A lot of them, definitely the bulk download type applications, maybe not so much, but the more interactive web type applications certainly are. And that you really are waiting for support in your platform, and some of those platforms and libraries already do support L4S. Okay, so once you've got an implementation, how do you make sure that it's working well? This is not just a simple set of tests. You really have to think about network performance. in a variety of conditions. We've seen a couple of presentations, just the last couple of presentations from Mohit and Koen, showing some of the scenarios that people think about when they're testing AQMs and congestion control. There's a series of events that have been conducted over the last few years to give application developers and network equipment manufacturers an opportunity to test their equipment. There's a series that have been run at the IETF hackathons, 8 of those. At CableLabs, we've hosted a series as well in our labs. So far, there have been over 20 companies and organizations that have participated with congestion controllers and receivers and network equipment implementations as well. If anyone is interested in attending those coming up, these are free opportunities, both at IETF and at CableLabs. Next one at CableLabs is end of February, and the next IETF one will be in July. So what's next? As I started out, 2025 was a big year for L4S. Lots of deployments coming along. 2026 is likely going to be even bigger. Like I mentioned, there are quite a number of network operators who are in field trials with L4S equipment today and will likely be going to full deployment very soon. So looking forward to seeing it really take off in 2026. So that's it for me. If there's time, we can do some Q&A.
Right. Thank you very much, Greg. I think there are some questions. Yes. So Tui Nien is asking, does L4S implementations require more compute or more computational requirements embedded in existing network infrastructure hardware?
More computational requirements, I guess it depends on compared to what. Certainly requires a mechanism to mark packets as they flow through the network. Requires the ability to differentiate between L4S and non-L4S applications, either via dual queue, like Koen was showing some results from a dual queue mechanism, or via FQ. There are some requirements around packet processing related to that, and the packet marking as well. So compared to maybe a FIFO implementation, certainly there's a bit more involved. Compared to an existing AQM implementation, whether that's FQ Coddle or FQ Pi or single queue Coddle or Pi, there's not a significant difference in computational load there.
Right. And then let's see. So DJ Lal is asking, is there a long tail of platforms that could benefit from sender-receiver enablement of L4S? Saying like you sort of listed the big ones, and is it trivial to test and be confident that the low latency application is taking advantage of L4S?
Yeah, so I think the libraries that are available for implementers to make use of can really help out the smaller application developers who may not have the resources to study congestion control design and do the sort of heavy lifting around implementing L4S. I think that's going to bring a lot of the long tail over time. Certainly, those applications may be the ones that that might wait for more at-scale deployment in networks. So you've got a couple of large operators that have deployed it and more that are coming. So as that percentage of networks that support L4S grows, that's going to be a higher priority for some of those smaller application developers. Also, I think the WebRTC piece helps out a lot. So there are a lot of applications that may work, or browser-based applications that are aiming for real-time streaming to the browser, and so support for L4S there helps out a lot. In terms of testing, that's been a challenge. There are so many different scenarios that are interesting and important to test, just because of the variability of the network and variability of conditions. So there is well, the interop series obviously is a good way to get a start on that. There has been some work on developing a network technology agnostic test plan for at least network equipment to test support for L4S. Same doesn't exist on application side, but so that maybe is an area of future work.
But I guess for sort of verifying that an app takes advantage of it, you can at least check that they apply the right markings to the packets and things like that, right?
Certainly, yeah. There are some easy things that you can verify, both for the application and the network. But yeah, getting beyond that, things get a little bit more complicated, right? With introducing competing traffic and ensuring that the new application is responding in a reasonably fair manner to the congestion mark, so it's not dominating the connection. So
makes sense. Right, I think there are also more questions. If you have time to look at the Q&A tool, that would be much appreciated. And again, Thank you very much, Greg.
Yeah, thank you.
Next is Jonathan Newton, Distinguished Technical Expert at Vodafone, shaping strategy, innovation, and best practice in fixed broadband technologies. He is also co-director of the Broadband Forum's Network Architecture Work Area, which coordinates several initiatives related to measuring and improving latency. So John, over to you.
Thanks, Bjørn. Hi, everybody. So this is a quick look at the Broadband Forum work. Just be aware it's not a complete view. There's a lot that goes on at the Broadband Forum that I won't be covering. But generally, right, something to avoid. If you've been following this series of webinars, then this probably won't be news to you. But we want to avoid this kind of situation. Lots of people have been in this situation, excited with the new service. Great, got your 1 gig, 10 gig service. Do the speed test, look at how fast it is, download a few things, prove that it's really great. And then slightly further in the future, maybe a couple of days later, well, is it really what I was looking for? Is it quite perfect? Things aren't working exactly as I anticipated? The overall issue is fundamentally that, as we know, user experience is not only related to capacity. There's lots of things that it can be related to. Whether the line is up during the time when the person wants to use it, or even just how well the person's day has been going that day, did they get out of bed on the right side? But latency, we know, is a key contributor to the end user experience for a number of applications. So it seems I'm speaking on behalf of the Broadband Forum, a very, very quick view of what we do. There are 4 things that the Broadband Forum does. One is around global open standards. Another is around certification and performance testing. We have a number of open broadband projects. These are open source projects relating to the specifications. And we have industry outreach in our base seminar series. And a lot of members, which is a fantastic thing when you're looking to kind of collect information around sort of service providers, innovative vendors, people with creating sort of ecosystem enablers. And if you're not on this list, then maybe you could consider it. So with the Broadband Forum, with that level of engagement from the industry, when we look out at areas of growth for broadband service providers, so over the next sort of few years, this is an area where service providers think they will be investing. And it's not a surprise to see quite a lot of autonomous networks, agentic AI-based, API-based developments, security, etc. But it's clear that if you ask service providers, they are still focusing on QoE, and they expect to focus on QoE in the coming years. And potentially some of that is down to the work of this community, looking at latency, looking at how that can be improved, and the fact that just capacity isn't necessarily the whole story. Really, this just reinforces the same point. So we're seeing then that looking at how you're going to differentiate, well, yes, 72% would say we're going to differentiate based upon quality of experience. Exactly how? I mean, that could be marketing based upon the quality of experience you used to have on a service. It could be some form of SLAs, etc. But the key is that quality of experience is reinforced as a differentiator moving forwards. So, what about challenges for latency? Take a step back. Let's come back to latency and look at how would broadband service providers look at it, and what are some of the challenges that they might have. First one is around visibility. Service providers don't always have an end-to-end view of the latency, the delivery. They might be able to tell from the server to the client what the latency is, but they don't necessarily have a full visibility of that on an end-to-end basis, and all of the segments. And the segmentation is a really important part. So understanding what is the latency in a particular segment of the network. That could be on the Wi-Fi, that could be in the aggregation, in the access, but it also could be in wholesale access, areas of the network that are not in the control of the broadband service provider, where you have an access provider delivering, say, a layer 2 connection, and then that is purchased on a wholesale basis by a broadband service provider, who then needs to kind of understand, well, what's the performance, what's the latency across that third party, and how does it fit into our overall picture? Second area is around the understanding, that key question of how do you relate application outcomes to latency, and what is the right information to collect, and what granularity and timescales should we look at? There's plenty of information available from networks that might be aggregated at a 1 minute or 5 minute interval, but actually some of the latency effects are only visible if you look in at the few hundreds of milliseconds or tens of milliseconds level. So actually, what's the balance there in terms of looking at latency? And what is the cause? What is it that triggers latency issues in broadband networks? And that can be queuing and scheduling. It could be queues, can also be bandwidth allocation and time slot scheduling in different access technologies. So there's a few things that can be going on there. And then what actions can I take? What can I do about it? So one aspect would be improving the queuing and scheduling, things like L4S, for example. Another action can be automation. Well, actually, can I do some latency-aware traffic routing? Can I select a path through the network for an individual subscriber? And then there's another challenge that potentially will get more interesting over time, which is the workload placement. If we're looking at creating and deploying sort of AI capability for particular users or compute, whether it be compute or sort of NPU based, then where should I put it? And you kind of want to know in advance whether the location where you're going to deploy it will actually meet the needs of that service, rather than deploying it and then discovering later that it's that you haven't got it in the right place. So there's a lot of sort of things that you need to understand, and that broadband service providers are kind of challenged in. So what has the Broadband Forum been doing about this? There's a few things that we've been doing relating to these different challenging areas. So one is the visibility aspect. There's been work on maximum capacity metrics, so that's a UDP speed test. It includes lots of latency results, so you can look at the sort of the latency under load associated with that. The quality attenuation architecture, so that's the TR452 series, sort of covers the visibility and that understanding of linking application outcome to latency. But it also spends a lot of time looking at the demarcation requirements. So it defined how to measure in different segments of the network, and how to be able to to understand, for example, well, actually, I can measure at layer 2 across layer 2 access provider, and I can measure using sort of the layer 2 performance management tools, EFM, Y1371. We can measure in multicast environments. You could measure in generally using other active test protocols that operators would have deployed in their networks, things like TWAMP and STAMP. Then a bit more around the understanding. There's broadband service metrics work. There's some internal modeling work on latency on PON, which is really interesting going on at the moment. And then more work around in the service requirements work area happening around service and QoE definitions. And then in the actions part of it, well, two things you want, one of which is sort of frameworks to be able to take automated decisions and push those into the network. Another aspect is the actual capability to do that and to configure and control the equipment. So the standardization associated with that and the ability to at scale deploy things out to devices in the home, for example, using things like USB. And then there are other work in progress items around the ability to programmatically decide, well, how do I place subscribers in the network, and work on how to apply L4S into the fixed broadband architectures. And then one aspect that I haven't mentioned already, which I think is really important, and that's the standardization of the data. So it's all very well and good taking measurements, but if you can't pass them around between systems in a way that's standardized so that all systems have the same understanding of the data and can make sensible decisions from it, then we are kind of missing something important. And there's work there around the recently published quality attenuation measurement formats. And then you can also use the USP platform's ability in the device 2 data models to be able to kind of collect information, either poll or bulk collection of data from devices, the many hundreds of thousands of devices that you might have into your control out in homes. So this is sort of a different way of looking at what I've just been talking about. I won't go through it in quite so much detail, but it's really just showing, well, actually, we can, where the work would apply. So how you apply L4S to broadband networks fits sort of across the whole piece of the broadband network. But then you want to measure the latency in a way that can be composable, can segment different domains. You need to be able to pass it around in a way that's understandable by all the systems and everything that will work on it. You need to be able to define application requirements to link that to application quality or outcomes. And then you need this sort of ability to push things back down through the network, make sensible decisions, frameworks, and then push down any changes or required to update or control latency in the network. So a quick look then at L4S. There is an active piece of work in the Broadband Forum about how to apply L4S to broadband networks. It's ongoing. I'm not proposing to explain what L4S is here. There's lots and lots of people on this series that have done a great job of that. But fundamentally, what the Broadband Forum is trying to achieve here is about defining L4S support and how that can be implemented to the network. What are the most beneficial points? Where should you deploy first? How could you do it in a scalable way? And by scalable, I guess one thing around sort of a number of service providers who have implemented broadband forum architectures is that the sort of the service edge of the network can often be relatively centralized, which means you have sort of hundreds of thousands of subscribers or thousands or hundreds of thousands on individual devices. Now, if you want to do queuing and scheduling on those every single one, then that can be challenging. Lots of ways to work around that, but that's some of the aspects we're looking at. The data model again, how do you configure and manage it? How do you monitor it? How do you validate the delivered benefits? Because that's something that's really key to be able to understand for both service providers and for customers. And obviously we work with, we're certainly not the only ones working on this, and we're really leveraging the work of the IETF, WBA, CableLabs, etc., and liaising with them extensively. What's our current focus? So what are we looking at the moment? Well, I said the scalable part, but actually also the impact of layer 2 segments. If you have a congestion point in the layer 2 network, what do? Do you pass that information up to layer 3, or do you sort of notify that at layer 2? Lots of open questions there. And then we also have a situation where lots of operators use PPP, for example, over the top of the networks. Well, how do you pass the information at that point? A quick shout out then, there was an L4S demonstration. Broadband Forum did a Network X with a couple of members. Intel particularly implemented L4S AQM at scale with their DPDK framework. So that was really showing how you can scale up in a sort of for what would be a broadband network gateway congestion management, queuing and scheduling, hierarchical scheduling, and Nokia with L4S Wi-Fi AQM for managing the end-to-end latencies. Okay, so where are we then? Broadband Forum members, we're working hard, continue our focus on latency as a key aspect of the work. Really truly believe that open standards, collaborative projects deliver real improvements in customer experience, and that those engaged in the Broadband Forum benefit from sort of early access, technical input, and the ability to shape industry solutions. So anybody interested in getting more involved, please reach out and see the links there. Thank you very much.
All right. Thank you very much, John. I have a question about on one of your last slides. You had one of the goals of the Broadband Forum is to identify the most beneficial points for deploying L4S. Do you have like preliminary results or ideas about what the results of that might be?
It's yeah, and that's interesting because it fundamentally, and I think this has been mentioned earlier, the access is often the bottleneck for a subscriber, and that might be often that's due to the profile that a subscriber has purchased from broadband service provider. And the question then is where is that enforced? And it may be enforced in multiple different places. It can be in the broadband network gateway in the broadband network. There can also be impact in the access nodes. That's sort of if you're thinking from a downstream perspective. From an upstream perspective, then again, there's actually the upstream can sometimes be, or often can be more of a challenge as well, from a latency perspective and where latency gets introduced. So there are sometimes queuing and scheduling points there that can really benefit from having the ability to signal to the application if there is significant queuing and scheduling taking place, or any queuing and scheduling taking place. So it really boils down to the key areas are the home gateway, the access nodes, and the broadband network gateway. Those would be the ones for earliest implementation. And then moving on from that, then there can be benefits associated with some of the aggregation networks, the backhaul networks, etc. And then as you start to go further into the network, it becomes diminishing returns in terms of the implementation, with the exception of needing to be transparent to the L4S markings. Otherwise, the whole thing doesn't work on an end-to-end basis. That's
of course, yes, yeah. All right, thank you very much, John. And that brings us to our break. We are a little bit behind schedule. So the break will be just 5 minutes, I think. And so we'll be back in, 5 or 6 minutes. So, yeah, see you very soon. Hey, hey everyone, we are back. So welcome back, everyone. And our next speaker is Stuart Cheshire, Apple's distinguished engineer for networking. And Stuart has been fighting latency both in end systems and in the network itself for many years. And he's the creator of Bonjour, Bulo, one of the earliest internet multiplayer games, and the author of It's the Latency, Stupid. So Stuart, please go ahead.
Okay, hopefully you're seeing that and hearing me now.
That is all working well. Thank you.
Excellent, thank you. Good morning, good afternoon, good evening, wherever you are in the world. My name's Stuart Cheshire, and I've spent most of my career working on making computers and networks faster. People have always wanted to compile code faster, spell check their documents faster, perform image adjustments faster. Megahertz and MIPS used to be reasonable predictors of how fast your computer would do these operations. But in the world of RISC and CISC and multiple cores and GPUs, people have learned that just the number of megahertz doesn't tell you the whole story. In the early days of digital cameras, a camera with more megapixels would almost certainly take a better picture. But at some point, we found that other things matter too, like lens quality, color accuracy. The fact is, people will pay to get things done quicker and save time. Our job is to deliver network technology that actually let customers get things done faster. Back in the 1990s, going to a 9600 baud modem from a 2400 baud modem would fill a screen of text in 2 seconds instead of 8 seconds. That was a great upgrade. But in today's world, upgrading from 100 megabits to 500 megabits won't make a web page display 5 times faster. Increasing throughput has stopped making a difference. And I think everyone here already knows why that is. I have heard people say speed is great, but latency is better. I think this is self-defeating. It sounds like we're trying to trick customers into accepting slower service for some reason. That's very frustrating to me. What we're doing is the opposite. We're not trying to trick customers. We are trying to give customers more speed. We're trying to make things faster. And if we use the term speed as a synonym for capacity, we're not serving our customers well. We can't change how other people talk, but let's not perpetuate this mistake ourselves. Anytime you open your mouth to say the word speed, pause and think if you really mean throughput or capacity. The key point is that we've got to the point where more throughput does not make the majority of things faster, but consistent low latency does. Let's talk some more about consistent low latency. Throughput and delay are largely independent of each other. Whether your throughput is high or low doesn't dictate whether your delay will be high or low. When the network is lightly used, it is very easy to have low latency. Most networks manage that. That's not a challenge. And when the network is used close to 100% capacity, on many of today's networks, the latency gets much, much worse. And people take that for granted. They accept that. They assume it's normal for some reason. You can have networks that have terrible latency even when the load is low. That's just bad. Let's not talk about those. But of course, what we'd love is this. Can we have the delay low even when utilization is high? As I said, on many networks today, we still have the case where the latency when the network is idle is very different from the latency when the network's being used. And I've labeled those here as idle latency and working latency. Working latency is latency in normal working conditions when the network is doing something. You might also hear this called loaded latency, but I try to avoid that term. That sounds a bit too much like overloaded latency, and I could forgive people for thinking that we shouldn't expect an overloaded network to perform well. But we're not talking about unreasonable overload here, just a normal level of load that the network should be able to handle fine without degrading the user experience. So how does the latency vary between idle conditions and 100% capacity? Many people assume that delay increases linearly as the traffic level increases. But the reality looks more like this. At utilization levels below 90%, latency stays pretty low. But above 90%, latency starts to go through the roof. So why not just stay below 90%? The problem traditionally has been that the sender doesn't know where 90% is. It only knows it's crossed that boundary once delay and packet loss occurs, and then the damage has already happened. The rate management used by traditional transport protocols is like someone driving a car with a blindfold on. When they hit the barrier at the side of the road, they hear the noise and they correct their direction, but by then they've already scratched up the side of their car. If you've ever used a video conferencing app that gave you an error message saying call failed, that means it crashed right through the barrier without stopping and ended up upside down in a ditch. L4S is the technology that lets network protocols course correct before they hit the barrier, keeping latency low across the whole utilization spectrum. Some more on terminology. Sometimes we use the term congestion informally to mean what happens when there are a lot of people on the network or at a busy time of day. But in networking, congestion control means something specific. It is the algorithm a sender uses to determine the optimum rate to send. Congestion in this context is not something to be eliminated. That doesn't make sense. You can't eliminate the rate management algorithm that the sender uses. And if anybody tells you they've built a network that doesn't have congestion, don't believe them. While we're on the subject of technical terms that are easily misunderstood, be very careful making analogies. It's very tempting when we're thinking how things should work to relate things to day-to-day experience. And when we use words like congestion, we immediately think of rush hour traffic on the road, and everybody hates sitting in traffic. But that is very poor analogy. It doesn't give us good guidance about how to build networks because it doesn't work the same. You don't open your garage door and have 1 million cars stream out, but your computer can easily make 1 million packets. And packets in the network are easily duplicated, reordered, corrupted, destroyed, retransmitted. We can't do that with cars. So be very, very wary of thinking that human intuition will guide us about how to make a good network. And when we let that human intuition lead us astray, it leads us to bad solutions that don't work very well. If network congestion was like congestion on the roads, then adding an express lane where you pay more money to use it would be the solution. At the airport, if you're flying first class, you get to check in at the first class counter. These human intuitions come from faulty analogies that actually don't give us good advice about how to build networks. L4S has gone through an evolution. At first, people had not heard of L4S. Now people have heard of it, and I think sometimes marketing people assume it's just a new name for traffic priorities. Their network has traffic priorities, so if L4S is just a new name for traffic priorities, that means they have L4S, right? No. L4S is a new solution, not a new name for all the old solutions that have not worked well. So if L4S is not just a new name for giving certain traffic preferential treatment, what is it? The key thing to understand about L4S is it is not a demand of the network, it is a promise to the network. Traffic classes and slices and reservations, These are all ways of an application having a tantrum and stamping its feet and saying, I demand you give me special treatment. And L4S is completely the opposite. L4S is the application or the sending machine saying to the network, I'll make you a promise. If you tell me to slow down because I'm going too fast, then I will. And that partnership, the network giving the signal and the sender responding, is what stops us going over 100% capacity and having the queue back up. If you're writing an application today on iOS or macOS and other platforms too that runs over TCP or QUIC, most likely you get this for free because the transport protocol does the work for you. If you're running your own custom protocol over UDP, then you're opting out of using an off-the-shelf transport protocol, and part of that is that you then have to do this work yourself. But that's doable, and many applications have. Another concern I've heard is what stops all traffic from using L4S, as if it would run out. And if you think of L4S as being like the first-class check-in counter, like the express lane on the road, then it's a finite resource and there isn't enough for everybody. But it is not a resource. It's a promise. And if every application, if every sender in the world promised to be a good citizen, that would be fantastic. So yes, there is no limit. There is no reason to police it. There's no reason to limit its use. The essence of L4S is that flows agree to cooperate to keep queuing delay low. Now, you can do this with per flow queuing, and that's great. You can do this with dual queue, and that can make the implementation cheaper, and that is fine because all the L4S traffic signals in the IP header that it is making this promise to be a good citizen. The one thing you can't do is do L4S with a single queue, because you can't have traffic that is promising to keep the delay low mixed in with traffic that isn't making that promise. And that is fine. Both kinds of traffic can coexist. So I think there are two kinds of traffic, but there aren't 64. And everybody loves the idea when you say that we can give a custom service tailored for your application, that sounds really nice. But when it comes down to it, all applications want the same thing. High throughput, low loss, low delay. Some are more on the delay side of the preference. Some are more about getting that absolute maximum throughput. And that's why 2 classes of behavior is the right number. Now, I'm not here dogmatically saying that L4S is the answer. Maybe something else will be invented. What's key is that we measure the right metrics that are good predictors of user experience. And that's why I'm very happy that the Ookla speed test app now, as well as showing you throughput, shows you 3 ping times: idle ping time, ping during download, ping during upload. And those last 2 numbers are the ones you should look at. Last slide. This hardly ever gets mentioned, but people have asked about it. What is the S in L4S? We talk about the low loss and the low latency, and that's kind of obvious. We know what that is. The last one is scalable throughput. What does that mean? Transport protocols like Reno have a peak throughput that scales proportionally to 1 over the square root of P. And the consequence of that is that to get 10 times more throughput, you need 100 times more reliability. You need the packet loss rate to be 100 times lower. And that becomes a barrier as we get to really, really high speeds. And L4S enables linear congestion control algorithms where the proportion is 1 over P. And that unlocks that future growth. So 10 things to remember about L4S. And I think we have maybe 1 or 2 minutes for questions.
All right, thank you very much, Stuart. Let me see. The end of your presentation caught me by surprise there.
Oh, well, if we don't have any questions, we could move on to the next speaker, and the slides will be available online. So
there is
My
a
last slide
question.
was that cheat sheet. Okay.
All right. Yes. So Kevin Smith is asking, cellular radio networks may be a case where you don't want everything to be L4S because there are still applications that prioritize throughput over consistent low latency. And the wild, volatile nature of cellular means that those apps can make use of capacity spikes as they happen, while L4S apps continue to use a constant rate. And I don't know if was that the end of the question, Kevin?
I'm not sure if
Because
that's a question or a statement, but I
yeah,
agree with it
it ends on a comma. So I'm
So I
wondering
agree with that. Yeah, I agree with that statement 100%. And that's why I think we do want two traffic classes, not just one. We want the traffic that is okay if occasionally it leaves a bit of bandwidth unused because it wants to keep the queue short. And then we have the big download. You're downloading a movie onto your tablet to watch on a plane flight, and you need to get it downloaded fast because they're starting boarding. Then you want packets waiting in the buffers. So if radio spectrum becomes available, you've got a packet waiting right there to take advantage of it, and you don't let the radio go idle. And that's a legitimate thing to do for big downloads or uploads. So I think there's room for both, and the dual queue approach is great because it gives you the best of both worlds.
Exactly, yeah. Kevin also says that was just a thought, not a question, but I totally agree. And I think it goes to what Koen was saying as well, that it's kind of the classic queue can absorb whatever headroom there is, which for
Yep.
some technologies, like as Kevin gets to, the volatility can be quite extreme. So yeah. And then Wojciech Romek is asking, he's asking, is there a single metric that we can use to measure speed, or will it always be application specific? And I'm not sure I understand that question, but what are your thoughts,
Yes, I
Stuart?
do. When customers are making buying choices, it's very convenient to have one or two numbers to look at. When people buy cars, they look at horsepower or miles per gallon or cargo capacity. Distilling complicated decisions down to simple numbers is very helpful. And that is why we have been working on the responsiveness test. And I had that on one of my slides. When the PDF's available, you'll be able to see the link there. We're doing that work through the IETF. We are explicitly working on answering this question. What is a good test that is a good predictor of user experience? In other words, how fast can I load a web page? When I'm watching some streaming video, how fast can I jump to another chapter? When I'm watching YouTube, has the video and the little thumbnails on the right of other videos you might like. If you get bored of one you're watching, you click another thumbnail. How long are you watching that spinning wheel before the system can respond to that unexpected click? It didn't know you were going to click that, didn't know you're going to change your mind, but you click the mouse and now the stopwatch is running. How quickly can we get you that new video on the screen? And the RPM test is intentionally tailored to answering that question. It is still a draft, it's not an RFC. So if you read that and have suggestions how to make it better, please do. For those who don't know, the IETF as an organization is open to anybody. There's no membership fee, there's no contract to sign. So read the draft, send an email with your feedback, and that is as valuable as anybody else's feedback. Thank you.
All right. So thank you very much again, Stuart, for presenting. And next is Wim de Ketelaere, CTO of Excentis. Wim joined Excentis in 2000 and became CTO in 2001. And he's a worldwide recognized technical expert on IP-based communication systems, access networks, latency, and Wi-Fi, with extensive experience drafting and participating in standards development. So Wim, over to you.
Thank you, Bjørn. Good morning, good afternoon, depending on where you are. Let me see if the sharing works. Give me a sec there.
don't see your slides just yet.
Sorry, yes, now it should work. Yeah.
No, something's happening. Yeah, there we go.
Okay, so my talk will be a bit more about the practical side, focusing, of course, on the new Wi-Fi technology, Wi-Fi 7, not including yet any L4S, just some very basics understanding on this Wi-Fi 7. Sorry, I want to move forward. Okay, so how does Wi-Fi 7 in the end actually lower the latency? I mean, it's about low latency. And of course, with Wi-Fi 7, we mainly talk about also this new feature called MLO, and that's where I want to focus on for this short presentation. So just a quick summary of Wi-Fi 7. Of course, what does Wi-Fi 7 provide? It provides wider channels. Okay, we go up to 320 megahertz. I will not focus on that one. Means more bandwidth, more speed, whatever name you want to give to it. High audio modulation, again, same benefit, more bits per second per hertz. More speed. More spatial streams. Yes, sounds very nice. I would say from a theoretical point of view, because it also requires more antennas. So for real end user devices, initially for the smartphones, tablets, the additional benefit will be quite limited. But for backhaul, of course, or high-end devices, yes. Then I would say a more difficult one, on which I will not focus much, is more efficient resource units. I would almost call it fixing a bug in the previous standards, where from a scheduling point of view, in the past, you were limited to one resource unit, which makes it kind of difficult to optimally schedule something. By allowing more than one, you can do it more optimal. But then, of course, I think the most well-known feature of Wi-Fi 7 is this multi-link operation. Multi-link operation, what is it about? If you compare Wi-Fi 6E to Wi-Fi 7, even if your access point is a tri-band access point, supports 2.4, 5, and 6 gigahertz, and your smartphone also supports the three bands, even if you're at close distance, at any moment in time, your device is only using one of those three bands. Okay. When the device moves around the house, it might be that it switches band from 6 gigahertz to 5 to 2.4. But basically, it's using one link at the same time. What's the idea of Wi-Fi 7? Basically, that you have now multi-link, and that devices can use multiple of these links at the same time. Your device could be connected at 2.4, 5, and 6 and use it at the same time. I would say at least that's the big marketing story, if I may say so. And of course, yes, the standards support that, but practically, of course, I would say there are some caveats, okay? So first thing we've done in a real practical test, isolated environment, no interference, reproducible environment, real devices have two Wi-Fi networks. Okay. Devices were Wi-Fi 7, so maximum channel width, high audio modulation, but initially we disabled the MLO feature. Okay, so two access points, client 1 to access point 1, client 2 to access point 2, and we disabled the MLO feature. Second case, exactly the same setup, nothing changed, but on those same devices, we just enabled this multi-link operation. Just to be able to really compare them head-to-head, no device dependencies, no, I would say, on sensitivity levels, all that kind of stuff, antenna orientations, exactly the same situation. Now, first, I would say, thing that you need to be aware of is just looking at throughput, okay? In this case, it was TCP throughput measured. Okay, look at, I would say, the speed we get when you use only 5 gigahertz. Okay, in this case, a little bit below 2 gigabits per second. Okay, fine. Okay. Take 6 gigahertz only. Okay, one device, 6 gigahertz. Okay, we got a little bit above 3 gigabits per second. Hey, That's great. Okay, and then we enabled, I would say, MLO for the third measurements. What did we get? Well, even slightly less than the speed on the 60 gigahertz. While you would expect it, as shown on the right hand side, that actually with MLO, the device supported 5 and 6 gigahertz at the same time, or at least that's what the datasheet kind of said, that at least it's the sum of the 5 and the 6, but practically, no, it was not the sum. So, of course, why is that? Well, if you look a little bit further deeper into the Wi-Fi 7 MLO stuff, most devices, or most current devices, I should say, although they support MLO, they can't actually transmit and receive at 2 bands at the same time. It's this band or that band. It can very dynamically switch very fast, but simultaneous transmission or reception at 2 bands, it doesn't work. It's not supported. Device capabilities. So there's no real gain in individual throughput, okay? And, okay, the class of devices is called the enhanced multi-link single radio device. I will not go into too much more detail about it. That's not the goal of this presentation. Okay, but what about latency? Because that's what we're here to discuss. Well, so to do that, you have to look at the graph, basically. We generated a consistent load to each client of about 900 megabits per second. It doesn't make sense to overload everything because then, of course, you're measuring buffers and all that kind of stuff. So fair comparison, always 900 megabits per second per client. Okay. If you disable MLO, okay, then you get an average latency for the first, I would say, setup, access point 1, client 1, of about 8 milliseconds. Okay. Second, a little bit higher, a little bit less than 7. At the moment we enabled MLO, okay, in that situation, we saw this average latency significantly drop, okay, a little bit higher than 2 for both cases, well, between 2 and 3. So, of course, what is actually happening there, this was downlink, by the way, for information. The access point was, or the access points were observing, I would say, what's happening on the different bands. And for people all over the world here, we're in Europe, capabilities for the spectrum we have on the 6 gigahertz, unfortunately, is a little bit less than other parts of the world. So basically 2 full width channels at 320 megahertz, of 320 megahertz at 6 gigahertz, sorry, doesn't work. So what was actually happening, the access point decided to start using the 5 gigahertz band on the other, I would say, on one of the access points. And due to that, actually the MLO feature did bring an additional benefit. Instead of fighting for the bandwidth, and if you're overloading, you're always causing latencies, of course, basically decide, okay, I will start using these other bands, and it's a very dynamic nature. And the other access point that was in the air, neighbor access point in reality or something like that, was still operating at the same band. And by that, of course, the latency was significantly lowered. Okay. Now, if we look at the CCDF, the histogram, I would almost say, of the latency, we did observe still that, I would say, things are not yet ideal. Okay. So yes, average latency went down, but if you then look a bit at the, I would say, more numbers to look at the different percentiles and all that kind of stuff, it was certainly not the case for all these percentiles. Okay, so still, I would say, there's something there which is just not right. Now, if we then observed or investigated a little bit further what was happening there, is that if we look at latency, or the latency, I would say, over time, that we did see spikes in the latency where the average latency is quite low, okay? That, yes, we saw spikes that went up to, I would say, 70 to 75 milliseconds Short duration, but they were there probably because on the Wi-Fi 7 level, I would say the access point or client was still evaluating, hey, what do I do here? Do I dynamically switch to the other band again or stuff like that? And yes, this was causing, I would say from a high jitter, you could almost call it, spikes in the latency, which in the end did not, give that high benefit yet. Although, of course, what it does show is that, yes, MLO has the potential, and of course, this is only a very, very simple test case. 2 clients, 2 networks in the air, just to at least, for a first, I would say, check, hey, what can this MLO feature actually do? But once implementations become smarter, I would say, more, in a more intelligent way to make their decisions on which bands to use, which link to use, I believe that Wi-Fi 7, or this will prove that Wi-Fi 7 with MLO, also with some other features, can indeed lower the latency.
All right.
Any
Thank you very much,
questions?
Lim. I have a background studying the Wi-Fi protocol, and so I have a question about the MLO feature, which I've been wondering about. It seems to me that if devices start using more than one band for the same transmissions or concurrent transmissions, we might run into a situation where sort of the congestion on the different bands start being correlated, because kind of the assumption that makes it possible to have lower latency because you can leverage different bands is that the one of the bands might be idle when the other one is busy. But if all the devices start using more than one band at the same time, then they will all be busy at the same time. Are you thinking about that, or is that something you've seen in the testing that you've done?
Well, we didn't actually test already that much on that because most devices today do not support multiple transmissions at the same time. The multi-link feature is limited supported, at least that's what we observed. But of course, the thing is, of course, and that's why it's very important that we did this testing with 900 megabits per second on each, I would say, access point to clients, because at the moment you start overloading, then of course, yeah, you create latencies all over the place. Now, the benefit is if there's a certain amount of bandwidth that you need, let me put it this way, okay, and you stay below the threshold that was shown in the previous presentation, then you actually increase the bandwidth you have available to your whole system, I would almost say, by having this multi-link, okay? And of course, if a device at the moment that the packet needs to be transmitted, it looks at the occupation of that band. And to be honest, that's also not that an easy decision in practice, because if you decide to transmit something on 2.4 with a 20 megahertz channel because it's idle, well, half a microsecond later, the 320 megahertz channel might be idle, where your capacity is significantly more higher. It's not an easy decision, but still, I would say statistically multiplexing in the end, that's what's about the likelihood that something becomes available, and by that your latency gets lower, is higher. But again, making that decision in a smart way, that's where I would say the vendor differentiation will be, and there's certainly different room for implementations there. And it's logical that the Wi-Fi standard does not mandate exactly how to implement that, but doing that decision or making a smart decision, that's what will be the differentiator.
All right. And then we have another question as well from an anonymous attendee. He's asking, how do you deal with latency in backhaul in multi-link ops on easy mesh device? Which seems kind of unrelated,
I do not know,
maybe.
to be honest, the particular stuff on easy mesh in that case, but from a backhaul perspective, I would say the multi-link makes it so much easier from a backhaul perspective, because also there, if the devices did implement it, we call it, I would say, in the DOCSIS world, we would call it channel bonding. You have more channels available where to choose from. Okay, and there you just transmit on the first or the channel that becomes available. Maybe that's not the best implementation, but you understand the channel that you believe is the best one. If you can have a dedicated backhaul channel, of course, with multi-link, that's easier. In the US, I would say, if you have more frequencies available, that's a more likely option than Europe, of course. But maybe for backhaul, you combine a 6 gigahertz with a 5 gigahertz. Front haul, you keep to 2.4 and 5, because for your client, for your devices anyway, 6 gigahertz is still limited supported. So, yeah.
Right, and I also see we have some very good comments
Bjørn?
in the chat as well. Did you want to say something, Stuart?
Yeah, if I may, I'll make a quick comment. I think there's a really important key observation here. In this test, you found empirically that 900 megahertz worked, 900 megabits per second worked well. And that's great for the experiment. But in the real world, the question is, how does the application know? Because if you're uploading a video to social media, if you do 100 megabits, it's going to take too long to upload. And if you do 3 gigabits per second, then it's going to, as you say, overload the network. And this brings us back to L4S, is the vital technology, companion technology that goes hand in hand, that's how the application knows what rate it needs to send to stay under this threshold and get the good behavior.
But then following up on the same thing, I think the remark that Bjørn said is really valid, because if you look at the Wi-Fi channel, it's not the queuing latency. Well, that's solved by L4S, but the contention latency is the big, and the EDCA backoff is the big problem. And exactly if you have like 4 channels and you have 16 devices, and each uses one channel, you have contention of 4 devices in each channel, which has a reasonable latency, peak latency of a few hundred of milliseconds. But if you have 16 channels competing in all 4, 16 stations in all 4 channels, you have like seconds latency in each of those channels. And you will probably have so many collisions, and the throughput will go down and the latency will increase. And as long as you don't fully use the channel, you don't measure this, and that's a bit a problem with L4S. And MLO is not going to help that.
All right, thanks for pitching in to discuss, guys. I think we need to close the session now, though. So I want to thank again all the speakers, and to everyone who attended and contributed to the chat and in the Q&A. Thank you very much. Tomorrow is our final day, and I hope to see everyone again tomorrow as well. We'll have 9 speakers tomorrow. Today we had to cut the session a bit short because there were 2 speakers who unfortunately could not join today. And the registrations remain open, so that if you know anyone who might be interested, there's still time to register for tomorrow's talks. So see you back here tomorrow at 4 p.m. Central European time tomorrow. And thanks again for tuning in.